Welcome to Venture Step Podcast, where we discuss entrepreneurship, industry trends, and the occasional book review. There's been quite a few technologies that have changed and completely altered the way that we live and communicate with each other. The easiest of these technologies to talk about would be computers. Computers originally were the size of a car, and then we optimized the cost and the size of the technology required to execute tasks. Then that computer that was the size of a car is now within your home. And then the next step was phones. Similar things are happening with robotics. And pretty interesting, this paper that Meta came out with from FAIR, where they discuss digitizing touch. And the paper is Sparsh Self-supervised Touch Representations for Vision-Based Tactile Sensing. And that's what we're going to be discussing today. As robots, they have vision. They're integrating these LLMs for voice interactions / audio inputs that can be encoded to understand that audio, turn it into text, and then process it, then respond back with a voice. But one thing that we're missing is the generalization of touch. And so there has been quite a few proprietary or custom built models for touch, but they have been task based. So what that means is we would train a robot to do one thing very well. But if you try to do anything else, then it wouldn't work. And Meta saw a couple issues with how we're going about touch and this application. One of the crucial things is changing the way that the data is processed and what kind of data can we use. So instead of using supervised learning, they use self-supervised learning. I'll explain the differences later in the episode. Then they have another thing that they talked about. They talked about how everyone was building custom-made sensors and there was no standardization of benchmarks. What benchmarks are we collecting? How do we collect them? How do we store them? And then another piece was, okay, well, it's kind of difficult to integrate all these sensors to these benchmarks. So try to create an ecosystem, which is what Sparsh is. And today we're going to be discussing the research paper, some of the findings. Once again, for these type of episodes, I am not a robotics researcher or AI researcher. If you're very interested in the stuff I talk about, I encourage you to go to the paper and read it. It's free. It's online. The paper will be linked in the show notes, and you can read it on your own time. It's 32 pages. About 12 of them or 15 of them are of Sparsh, like the Sparsh paper, and then the other 15 or so pages is references and support to their research or stuff that they've been building on or built on top of or other people's work that was used in their findings. Okay, so that being said, we're going to talk about the limitations of the current touch technology, what Sparsh tries to solve, and what's the difference between self-supervised and supervised learning, some benchmarks that they created, and the implications of Sparsh in general. Okay. But before we dive in, of course, I'm your host, Dalton Anderson. My background's a bit of a mix of programming, data science, insurance. Offline, you could find me running, building my side business, or lost in a good book. You can listen to this podcast in both video and audio format on YouTube. If audio is more your thing, you'd find the podcast on Apple Podcasts, Spotify, or wherever else you get your podcasts. Okay, so the first section is the challenges of robot touch. I would say I talked about it briefly in the intro of this episode, but in a general sense, is there was an issue of being able to share data with others. There's an issue with how the data was being trained and the cost of the data and the limitation of of one, the access to the data and the expense of obtaining classified data. And then the other thing was like understanding these metrics that are being applied, right? So it was a little confusing at first because I am once again not a robotics researcher, so I had to look up these things. But some of the metrics they use is like poise, the shape and size of an object, the force applied to alter the poise of the object, the texture of the object, and things called slip. And all of those things need to be understood digitally before you can actually apply them in the real world. So all this stuff is being done in the virtual world. And that's what I was finding confusing was you have an image or a video, and that video or image would have this data overlaid on top of it to help predict the slippage or different class, like the way that you're clasping the object virtually. It might result in some slippage. And do you have the reaction time, or are your hands placed in the right way digitally to react to slippage? And if you're running at 60 frames a second and you are going off the normal reaction time of a human, you have about 80 milliseconds to react. And so there's all these weird things that are going on, and I find it quite intriguing because it's similar to how you would interact in the real world, or as a human how you would interact in your day-to-day, but you don't necessarily realize all the nuances when it comes to touch, and how your fingers can sense out with the texture of the object, and you kind of just know that, hey, when I pick this up and I grip it this way with this certain texture and the angle of which the object is shaped and its proposed weight given the texture and what the material looks like, I know that I can pick this up with two fingers, lightly grasp it, or if I really press on it, it's going to break, or these other things that are second nature. It's difficult. It's difficult to make that happen. One, virtually with this robot, and then also consistently perform these tasks without error, which is something else. So one of the key issues, that being said, all this stuff is related to how humans interact in their day-to-day world. One of the things that these programs were doing before was they were making their own custom models, and then they were training data, supervised training data. And so supervised training data is something that you would use in a regression model or classification. And basically that means that you have a data set. And I think the easiest thing is okay, is this a dog or a cat? You're not specifying that the species of not the species, but the type of dog. We're not doing English Mastiff and Poodle. We're just saying, is this a dog or is this a cat? Right? So you would just give your model, here's my images, my training set, and then you could partition it in certain different ways. Like you might do 5 partitions and split it XYZ, and then have your tests, your validation, your training, blah blah blah. But for this instance, we're just going to keep it really simple, and we're just going to talk about the actual training data, and how you go about training. So in supervised learning, you just have the data set, and then the data set has this metadata associated with like an image. So in this case, you have an image of a cat, a black cat, and then it'd be associated with it would be this additional data with like, oh, this is a black cat. And so then the model will know, okay, this is a black cat. That's what a black cat looks like. And then you just say that many times. Like you might have 10,000 images of black cats. And then after that, then you have the same thing for white cats. And then you have some for spotted. And then you have these dogs. And you've got a white dog, a black dog, a brown dog. And so then when you train your data, then it will know that, hey, this is a dog, this is a cat. Okay. But then what if you try to give the model a purple dog or some kind of cat or dog that it wasn't trained on? Well, then it doesn't work. Or what if you didn't want to train just for dogs, but you wanted to do dogs, cats, and maybe birds? Well, we wouldn't know what a bird was because it'd never seen a bird before. And so you have to have everything labeled and classified, which is very time consuming and expensive. Thus, there isn't that much data out there. And then if there is data, it's so cost prohibitive to allow other people to use it. And so it's normally closed source. So what Meta's doing is they made their own data set of like 475,000 textile images that will allow other people to train their models on. And then they changed the way that they went about it. So instead of using supervised learning, they use self-supervised learning. So the model has to understand the relationship between what the actual image is, what the relationship of the image is to how it interacts with the robot and touch, like with the different textures, the shape, the force applied to these virtual images and videos, and how does that affect all the slippage, and what about the different poises of the image. And so understanding all those little nuances, like how you would pick up an object in real life, they're trying to do digitally, which one is difficult and two, pretty cool. But it's way different than how typical approaches are being done. And then we have this data set that allows people to train their models on. And then Meta also came out with these models. And the general sense of this is, one, make it easier for people to play around with digitalizing touch. Like, get it into as many people's hands as possible. You never know what's going to happen with a curious mind. And then release a data set for the group, like for the the cohort of robotics experts, engineers, researchers, all those people. And then the last thing is generalize these tasks. Instead of being task training, transform this into a generalized training set so that there is no, oh, I'm training to know if it's blue or black, or if this is a blueberry or whatever. It will just understand. And the idea is just to understand your world and interacting with objects in your world, instead of just training for one object or a couple objects in this specified task. Train for everything. And then once you have a ground truth understanding of your interactions and where you are in this 3D space, then you should be able to understand how to do your task, which I find pretty interesting. But yeah, general sense, we had task specific models. We're moving to a general purpose model. And that's what a lot of people are going towards. Like these different researchers, like with Meta or with OpenAI or Anthropic or Google, there's a lot of papers being pushed out for general AI knowledge versus it being a task or something else. But yeah, that's what they're trying to do. Are they getting it done? I think that the research looks promising, like from the results of what they have and the general perception of the AI researchers or robotic researchers on social media. They seem very excited about it. In a general sense, it seems to be solving some crucial problems to moving robotics forward. This would just make robots more versatile, adaptable, and efficient. So there was a blatant inefficiency of private companies continuously training and gathering data and then creating their own custom models. Now we have this massive open public data set, and it's open for researchers to publish whatever things that they need to. And then it also would create a more versatile robot. Like, what if the situation changes, or what if the color of these objects that you're trained on are changed with different manufacturers, or What if the environment that you're placed in as a robot is slightly different than the virtual world? You got to be able to adapt, and you got to be able to think on your feet, a robot or not. Everyone's got to think on their feet. So I think it's pretty interesting, and I enjoyed this paper. But one thing it didn't explain was the visualization of touch, which is the vision-based tactile sensors. It's quite interesting. So they have with markers and without markers. And with markers have these little dots on the gel. It's like the squishy gel thing. And there's little dots on I would call them nubs. We just call them gel nubs because it's like think about it as a little finger nub, like the first nub of your finger. Little gel nubs, little robot gel nubs. And there's little markers on them, like little dots. And those dots are pushed, like when you touch something, think about the tip of your finger. When you touch like the little skin on the tip of your finger, it kind of changes a bit. Like you could see how it slides or it presses against the object that you're holding. Same thing with these little gels. And so the gels with the markers understand, okay, the one of my points up on my gel nub moved from this position to another position, and there's some light reflection and these other things going on. So okay, this was the amount of touch, this was the amount of slippage, this was the amount of force applied before slippage happened, and then when I released my grip, this is when slippage started. And so it's able to mathematically understand the interactions between the robot gel nubs and the robot's grip and the object that's touching. It's pretty cool. I think you would explain it as like a little gel nub that's squishy that, you touch it, the gel deforms. And then when the gel deforms, there's measurements taken. And from there, that information is processed, encoded, and then stored. And then later on, there's analysis done on how it worked, what worked and what didn't work. Okay. So that was that. We talked about the new approach of to tactile sensing, the self-supervised learning, and why it's important. It's an important approach, and it allows you to not have all the answers, and it's described as a teacher student situation where the student, which is the model, like there's two parallel models. One has some of the answers and then one doesn't. And then the teacher is teaching the student, and then the student has to use the teachings from the teacher or the professor to get a result similar to what the teacher would have gotten. And it's good at like things like predicting like missing parts of the image, understanding images that aren't labeled, grouping similar images, like classifying, okay, like, all right, so I don't know what this thing is, right? These are all animals with 4 legs, and they're similar sizes, and the hair texture is similar. I think that these all go together. And then you put those. Okay, and then I've got this metal looking object with 4 round circles at the bottom. They're all different colors and different shapes, but they all have similar texture and look the same ish. Like the outline of it looks the same. And then you'd be like, oh, that eventually you find out that's a dog and those are cars. And so it's able to understand and better than supervised learning, because self-supervised learning is kind of how we would go about learning as humans. And that's why one of the reasons why I find this stuff intriguing is these papers are a reflection of oneself. Like, these things are trying to mimic humans, and then it makes you think about yourself and your interactions as a human, and how everything could be mathematically measured, like emotions, touch, knowledge. I don't know. I mean, I just find it interesting. So I don't want to go on a tangent. I want to stay focused because this might get long. But they have the self-supervised learning instead of supervised learning, and then from there they were able to experiment with different approaches. So they had self-supervised learning, then they had self-supervised learning with image modeling. And what is that? So mask image is what it sounds like, where you hide parts of the image. And so maybe you hide 3/4 of an image and it's got to figure out what the image is. If you have 3/4 of it covered and it's like some kind of berry looking thing, and then you predict, oh, this is a blueberry, and I only can see 1/4 of it. You have to figure out, depending on the texture and the shape of it and how it looks and blah blah blah. Oh yeah, this is a blueberry. And then there's a combination of approaches, but they came out with 3 models and they all have different strengths and weaknesses. But for the most part, are they're pretty close in certain areas, and then in other edge cases, one is better than the other. But they have Sparsh MAE, Sparsh Dino, Sparsh IJEPA. They have different strengths and weaknesses, and the general sense is that each of which are a tool, and they're not necessarily one is better than the other for everything. It's just the kind of thing like, oh, what program language is the best? Like people get really caught up with, oh, is Python or R or Java or Go or Colon or whatever the language is, Julia, which one's the best? And people get really caught up on it, especially in college. They're like, oh yeah, like Python's the best. You could do everything, but you're not the best at anything, but you're probably second or third. So the Python's the best general purpose language. And the other people are like, oh, well, C++ or C# or whatever it is. They all have their own little nuances of what they're really good at and what they're not so good at. And you could potentially do anything in any language, but it doesn't make sense. Kind of the same thing here. Not as extreme, but close enough. And then they made this other thing called TACbench, and they standardized a benchmark system for evaluation of touch representations. And the things that they did was they standardized slip detection, poise, grasp, stability, texture recognition, force estimation. So when you see an object, like how much do I have to press on it for slip? How do you detect? How can the model properly detect object slipping digitally? Poise estimation, understanding where this object is in a 3D space, and getting that right, and understanding how far or what the distance is between you and the object. Grasp stabilization or grasp stability. Texture recognition, understanding the texture of the object and how that might affect, one, how much force is required. Two, how will that affect your grip, which would affect your slip. And then the bead maze problem, which I had no idea. I was looking it up on the internet. I was like, what is this? I've never heard about this before. And a bead maze is some kind of toy, children's toy, that's used for hand-eye coordination. And basically it's like a wired toy that has beads on it, and you try to get the bead through the maze. And they do the same thing with the robot, which sounds like torture, because they don't train it on like what's the right answer for the bead maze. They kind of just train it on different images of the bead maze, with the bead being in different places on the maze, but they never trained it for the answer. And so it just sounds brutal, where the robot's just having to figure out, one, because it can't really see, right? Like, you got to think about it. Like, it's like a blind man trying to go through a maze with only its hand. And so it's in the dark. can't see, it only has is his hand. And so it could feel that, one, I am pressing on the bead, I'm holding it, and I'm moving with little resistance. Okay, so this might be the right answer. And then you keep moving, and then there's resistance that comes up. Oh, that's the wrong answer. Okay, let me go back to where I started. Okay, let me try this way. Oh, that one doesn't have resistance. All right. And then it keeps doing that over and over and over and over and over. It just sounds like torture to me. And then there was this other thing that they were talking about, which was model video tubing, or tubing video modeling is a technique of hiding an image, like 30, not an image, video, sorry. Hiding like 30 to 40 seconds of a video randomly and cutting it all out of the video and having the model predict like what happened. That sounds brutal as well. Some of this stuff just sounds straight up like torture. This bead maze thing just sounds excruciating. I would never want to do that. I couldn't imagine being blindfolded and then having to navigate a complicated maze with only my hand. Not cool, Meta. Not cool. So then, yeah, how does Sparsh understand these tactile images? Well, it standardized. Remember, it's standardized. It has a standardization benchmark. It understands and was trained on data, textile data, and then so once it's in action, it's basically just understanding and visualizing the force fields, understanding and that includes this kind of weird-ish. They had two comparisons. One was the previous method of how other companies or methodologies go about it, and when you touched an object, it would come back with a whole bunch of metrics and numbers. The way that Meta did it was they kind of have a pixelized, not image, but like a pixelized grid map. And then to understand the force and the force manipulation that was required, it would have a heat map of where the object was touched and then how hard, how much force was put onto the object with the grip, and where was it touched and how was it touched. And so then you can kind of measure, okay, you grabbed the object here, you slipped, or you didn't grab it hard enough, and then you can understand like what was going on and what was going wrong. Their method makes a lot more sense than the other method. The other method was like overly complicated, and you couldn't see like where it was being touched and how much force. I mean, you could, but you couldn't visualize it. So visualization is always easier to understand when you're trying to translate localized data, like localized data meaning what the robot was potentially be touching, and then putting it back onto a computer and understanding what happened previously when you weren't even there. So general sense, you're utilizing one, the generalization of touch. You are standardizing the benchmarks required to understand what touch is, and then you're visualizing how the touch interacted, how your grip interacted with the object. So understanding, what's the right amount of force with preventing damage, but also not enabling slippage. How do you manipulate objects without crushing them? Performing tasks that require precise control, like assembly or surgery, which it comes in this bead surgery problem, or the bead maze, which sounded not so fun, but I guess it's important for the robot. I don't want to be doing it. So has this stuff worked? Yes, it has. And if you listen to the last episode, I talked about how it was like 93% better than the other methods. And so it's been outperforming traditional force estimation models. And that is a factor of, one, standardizing the data, two, having a generalized approach with self-supervised learning, which is different than supervised learning, and then understanding and visualizing these touches. and how this works. I think that would give you a general sense of how this podcast worked. I could go into more detail about poise, slippage, or these other things, but I think that you guys, listeners, would have a good grasp of what's going on. And I think I provided enough information for this podcast episode to be useful. And I don't want to necessarily ramble. I want to make sure that it is concise, to the point, and gives you a good understanding. And if you want to go a little deeper, then you can, of course, with the paper. But I encourage everyone, if you're interested, to read the paper. I think it's a well done paper. I still think that the best paper of the year that I've read is Herding the Llamas. Herding the Llamas. It always sounds like herding, like I'm herding the llamas, but I'm herding the llamas. That's the best paper I've read this year, by far, by a long shot. So if you haven't read a paper and you have a yearning to read one, I would read that one. It is quite dense. It is almost 100 pages. I think it's 95 pages. Give it a go. So fun. Loved it. Loved every minute of it. This paper also is quite good. Very energized I became last week. I had COVID and was struggling. Today didn't have that much energy. I'm still behind on the podcast, where I'm recording a podcast just before it's supposed to come out. And I was like, I just worked late and didn't necessarily want to do this podcast episode. But I read the paper and I was just so energized with the knowledge and intrigued and just overall fascinated with the information and how they went about solving the problems that they're researching and trying to provide the free market. Overall, thought the paper was great and they explained everything. And then I didn't go through it on this side of this episode, but maybe I could in a future episode. I didn't deem it worth talking about, but at the back end of the paper, they talked about the different splits, the explanations of using different type of modeling techniques and which models they use and how they went about it, the splits of their data, reducing how the model performed on different types of data, if they reduced the amount of data they had. And I thought it was quite interesting, the difference of the performance when you trained on 1/3 of the data, half the data, or a tenth of the data. And it seemed like in certain scenarios, you could get away with only training with a tenth of the data. And it's only like a 0.5% or 0.5% a difference. And I was like, yeah, that's decent. That's grand. So there's some cool snippets that I didn't necessarily get to talk about in this episode. I didn't want it to be a 2-hour episode of me just talking very technical. But once again, I encourage you to read the episode. And if you thought this podcast was interesting, give me a comment and let me know what you think, what you found interesting, or if you have any additional insights. If you've worked in this space. Once again, I'm not a robotics researcher. I do not work in computer vision. I work in insurance, but I did find this paper quite interesting. And just overall, I encourage you to interact with the podcast episode and or look into the research paper provided in the show notes. Next week, we're going to be discussing the next research paper, which is going to be, I think, the CoTracker or CoTracker 3, or maybe another one. I don't know. I have been taking your guys' input very seriously. And so one of the things that I've gotten, I wouldn't say roasted about, but that people have talked about was make sure, and other people like my mom or others, they're like, make sure that you like look into the camera and make it seem like we're having a conversation, which I've been working on. It's more difficult. I had a bad habit since I work remote and I'm not always on camera. I typically try to, like, for big meetings, but I'm not always on camera. And so I just had a habit of like looking around when I was talking and just looking at various things. I'm not necessarily looking like I'm not paying attention. It was just a habit of just moving around. So I've been very focused on talking to the camera, and I hope that, one, you appreciate these changes, and two, I hope that you feel that I'm listening to you. Although I am not some large YouTuber or content creator, I do read the comments and I respond to everyone's comment, unless you're a bot. If you are a bot, then I just will respond some nonsense back because you're sending me nonsense. But otherwise, I will respond and engage, and I'll listen to you. Some comments aren't that nice. Some comments are nice. It's fine. You put yourself out there on the internet. You're going to attract all sorts of people. It's okay. So that being said, I wish you a good day, a good afternoon, good evening, good morning, wherever you are in this world. Thank you for listening, and I hope that you tune in next week. See ya. Bye.